Welcome back to the discussion of this, particularly this atmospheric boundary layer in connections with wind shear. So we have kind of talking about how this profile that um, can be represented in the lower close to the Earth surface. So there are two ways. I mean, if you look at the ongoing discussion on that, so we have talked about that this is primarily arising because of uh, this profile that which are turbulent in nature, and the mathematically we can represent this. One is that log law or logarithmic profile. The other one would be power law that we would talk about here. So, and then this was our discussion point, and we kind of arrived at this logarithmic profile. But here one can see the integration is from z naught at the surface, not zero. Okay, and that because any natural surface are never uniform and smooth, because any natural surface are never uniform and smooth. So that's what you kind of integrate between. So this, so you can have, let's say, different kind of fields you can have, like let's say some terrain. You can have open area. You can have like uh, so different surfaces have different Z0 values. So that kind of provides you an information or idea about the roughness, because this Z0 is kind of taking care of the surface roughness. So if you have terrain, if you have trees, if you have buildings, if you have desert area, if you have some hills, if you have some small forests, I mean, there could be a different surface, so that one can of estimate that. This equation here we can rewrite in different forms. So we can do ln of z k of u star u of z plus ln of z naught. So this is what can be plotted on a semi-log graph, and the slope of is kappa by u star. Okay, and from a graph of experimental data, u star z naught can be calculated. So this log law is often used to extrapolate wind speed from a reference height, okay, to any height at z or to another level using this following relationship. So what we can do, let's say u of z by u of zr, that would be ln of z by z0 ln of zr by. So this is a little bit of kind of an algebraic reorientation of this whole thing, so that you can use it. Also, sometimes it can be modified to consider mixing at the Earth surface. So sometimes it is modified to consider mixing at the earth surface. So we can express the mixing length, let's say L, as kappa of Z plus Z0. So then my log profile becomes U of Z, U star by kappa ln Z0 by Z0. So this is what you can get, and you can use this thing. So what we can use, the second one is, so second option is that we can use power law profile. Okay, so power law represents a, so this represents a single model, I mean simple model, rather simple model for the vertical wind speed profile. So this kind of represented as U of Z, U of ZR, Z by ZR to the power alpha. So here UZ is wind speed at height of Z, UZR is wind reference wind speed at ZR, and alpha is the power law exponent. Okay. So which is very common in the turbulent flow profile. I mean certain conditions this alpha could be, for certain condition alpha kind of 1/7. So it indicates a correspondence between wind profile and the flow over a flat plate, which was done by the great scientist Listing in 1968. But in practice, alpha is a variable quantity. So obviously alpha would vary with some kind of an height and all these things. The dependencies of alpha could be parameters like elevation at the time of the day, time of day, season, nature of surface or terrain, wind speed, temperature, various thermal mixing parameters. Okay. People, I mean, many researchers feel that this complicated approximation reduced to a simplicity and applicability of the general power law that wind energy specialists should accept the empirical nature of power law and choose value of alpha, the best fit available wind data. So there are, in a typically the thing is that in turbulent flows, depending on Reynolds number, this alpha parameter can vary I mean, it's 1/6 to 1/7 and all these things. So here also the flow that is being represented as a turbulent flow. But one can see for this particular case, alpha has a lot of dependencies like elevation, time of the day, season, nature of the surface or the terrain, whatever, wind speed, temperature, various thermal, mechanical mixing parameters. So what researchers have suggested that the best possible fit for the wind calculation that should be used. So there are certain correlations which are already or which already exist, which can provide a best fit for this kind of alpha variation. And if that can be taken into this power law profile, probably that represents the more generic situation or solution for that kind of a scenario. So some of these are your here the first, alpha is only function of, let's say, velocity and height. So if you consider that, then one way of handling this type of variation, this was proposed by Justus in 1978. So the provided expression is that alpha is 0.37 minus 0.088 ln of U reference 1 minus 0.088 ln of Z reference by 10. So here U is meter per second and Z is in meter. So this was given to consider the velocity and the height. So you get some variation of alpha, which can be used to estimate that. Then there are correlation where correlation based on the surface roughness. So alpha is a function of surface roughness. Okay. So this was kind of proposed by Conyan in 1975. Okay. So this includes alpha is 0.096 log base 10 Z naught plus 6 log 10 Z0 square 0.24. So here this is kind of an validity here is that Z0 valid between 10 meter to 0.001 meter. Okay. This is the range of validity where Z naught is surface roughness. Okay. Which is in meter. So you can get this thing. So there are another option where you have alpha is a function of both surface roughness, velocity. So this is what, so this one can find by, this was proposed by NASA researcher, and you can look at the reference of FRIDA, which tabulates some kind of that kind of variation. So even in the Paula profile, you can have different correlations. So that simplifies the dependency of the alpha, which we have talked about, that there is a multiple dependencies of alpha, like elevation, time, season, and all these things. So it can reduce to some kind of a correlation. Okay. So uh, that would now the issue is that all these two things, that logarithmic profile or the Paula profile, they try to, so these two approach, they try to provide the basically velocity profile close to surface. So essentially that takes into account the atmospheric boundary layer. And to accommodate the atmospheric boundary layer, either you use this kind of logarithmic or power law of some kind of profile. So using that, what happens is that you would, using this, you can have predicted profile, okay, and there is an actual data. So this is important to characterize this variation between the predicted profile and the actual data, because eventually this is going to kind of contribute towards the estimation of wind shear for a given site or all these things. So typically what has been seen that these profiles are quite a good fit to predict wind shear under most of the generic condition, but wind shear can change by, let's say atmospheric stability. Then you have surface roughness. Then change in surface conditions, terrain shape. So all this can change. I mean, obviously, you can think about all these are going to, I mean, in a one hand, these are going to impact on velocity profile. So that in turn will going to affect on wind shear. So it's a situation of some kind of an closed loop where now one can quickly look at the effect of terrain on wind characteristics. I mean, so the terrain effect would include, so this effect that include velocity deficit, velocity deficit, unusual wind shear, and also you can have wind acceleration. So the terrain can impact in that fashion. So this would impact the velocity profile, unusual shear, and all these things. So the influence indirectly affect the turbine power output. So that kind of lead to the site selection, other economical aspects, etc. So there is a kind of an connectivity among all these effects. So I mean, we can on one hand say that okay, mm, we have terrains and all these things, but eventually it's going to impact your turbine power output. And once that is impacted, you tend to look at it that which site is to be selected, whether the other viable conditions or for the economically viable. So there are different classification of terrain. So if you the terrain types, if you classify, so there could be a two major classification. One could be flat terrain, or you can have non-flat terrain. So sometimes this non-flat terrain also termed as an complex terrain. Okay. And flat terrains is terrain with small irregularities such as like forest, shelter belts, etc. Okay. Non-flat terrain has large-scale elevations or depressions such as hills, ridges, valleys, canyons. So once you try to classify these flat or non-flat terrains, there are certain conditions that must hold. So for flat terrain to be considered as a any irregularities on surface or the terrain to be considered as a flat terrain, you must hold. So one is that the elevation differences between the wind turbine site and the surrounding terrain are not greater than about 60 meter. So essentially in an radius of 11 or diameter of 11.5 kilometer of the turbine site. So within that, the elevation difference between the wind turbine site and that should be very less. Then no hill has an aspect ratio not greater than 1 by 50. That is again within 4 kilometer upstream and downstream of site. the elevation difference between the lower end of the rotor disc and the lowest elevation on the terrain is greater than 3 times maximum elevation difference. So that is within 4 kilometer of upstream. So these are the conditions kind of one can consider this to be a flat terrain. So similarly, non-flat or complex terrain, so that can have variety of features. So if you talk about the non-flat one, then that has, you can have isolated elevation or depression, be mountainous terrain. Okay. So these are obviously we do have different kind of, so flow conditions in mountainous terrains are complex because the elevation and depressions occur in random fashion. Flow in such terrain can be divided into two classification, small and large scale. Obviously, the distinction between these two be made with comparison to the planetary boundary layer, which is assumed to be about 1 kilometer. So one important point to be made here is that information on wind direction should be considered when defining the terrain classification. For example, if an isolated terrain which is 200-meter high and 1,000-meter wide are situated 1 kilometer south of the proposed site, then the site could be classified as non-flat. If, however, the wind blows only 5% of the time from this direction with a low average speed, say 2 meters per second, then this terrain should be classified as a flat terrain. So, point here is that this flat and non-flat terrain can be also varied depending on the conditions where your proposed site is, and then what is the wind direction is. So wind direction also plays an important role here. Depending on the wind directions and which is the radius or whether it's the upstream or downstream of the site, that would also going to identify or helps to identify whether it could be flat or non-flat terrain. Okay, so we'll continue this discussion on the terrain more. We'll stop here and continue this in the other session. Thank you.